So our last speaker will be about circuit optimization. Raghav Malik is, I believe I noted he's looking for a postdoc. Is it correct? Yes. And will tell us a bit about synthesis, or at least optimizing some specific kind of circuit using some new tricks.
All right, yes, okay, sounds like I'm audible. Great, all right. Hi, I'm Raghav. I'm currently a PhD student at Purdue. And today I want to talk to you about this technique called arithmetic lookup tables, and in particular, how we can use these to optimize circuits in the context of homomorphic encryption. So this is work that I did with my collaborator Vedant, and my advisor Milind. Okay, so if I'm going to tell you about homomorphic encryption circuits, I should maybe start by giving you some background on what fully homomorphic encryption is. So fully homomorphic encryption, or FHE, essentially refers to any encryption scheme that allows us to evaluate functions directly over ciphertexts without having to decrypt these first. So the usual sort of setup for this is we've got two parties, we'll call them Alice and Bob, and maybe Alice has a couple of inputs, x and y, and she wants to compute some function f over x and y. So she wants to get back like some computation of f of x, y. Different homomorphic schemes have different ways of thinking about what we really mean by function, but for our purposes, for now, we'll think of functions as being represented by some kind of circuit that we want to evaluate. And then by encrypted data, I mean like ciphertexts. Okay, so the way that this protocol proceeds is Alice starts by encrypting her inputs using some homomorphic encryption scheme. She can send the ciphertext over to Bob, who can then use the homomorphic capabilities of the scheme to compute some function f of x, y. In particular, Bob gets back an encryption of f of x, y, and then he can send this encryption back to Alice, who can then decrypt it with her private key and do whatever she wants with the result. Now, this sort of setup is very useful because Bob never actually gets to see the values of x and y, right? So Bob knows that he's computing some function f. He knows that it takes two inputs, but he doesn't know the actual values of x and y. And so in particular, this is very valuable for cases when, like, let's say, companies want to perform computations on like private user data. So for example, like Microsoft uses this in Microsoft Edge, password monitor. They sort of use this to like detect when your password has been leaked without sending your password over the wire in plain text to these like databases of leaked passwords. Okay, so homomorphic encryption is kind of a useful thing that we might care about. But the big problem here is that this actual encrypted computation is incredibly slow, right? So in particular, computing over ciphertexts can be like several orders of magnitude slower than just doing the same thing over plain texts. And so really what we want to do in this paper is ask the question, can we make this faster, right? Can we actually help Bob by making his part of the protocol a little bit more efficient, help him like compute this function more efficiently? So the particular contributions that we make, first of all, we developed this notion of an arithmetic lookup table, and sort of show how we can think of this as like a new programming abstraction for certain kinds of homomorphic encryption schemes. And then we show how you can actually build a compiler that knows how to use this abstraction to generate smaller and faster FHE circuits. So if I'm going to tell you about our new abstraction, let's start by talking about the old abstraction. As I mentioned before, there's a lot of different FHE schemes out there. The particular one that we're going to use in this talk is called CGGI. The letters here stand for like the names of the people who came up with the scheme, but that's great. So the traditional CGGI programming model sort of assumes that our ciphertexts are encryptions of bits. So this is like encryptions of ones and zeros. And the sort of workhorse of computation here in the scheme is the ability to evaluate arbitrary logic gates over these bits. So with these capabilities, maybe it's kind of clear how we can proceed. We take whatever function we want to compute. We use standard like Booleanization techniques to turn this into one big Boolean circuit. And then we just evaluate the circuit gate by gate over our inputs. Now, optimizing this circuit, or like making this run faster, since the only thing we can do is like evaluate one gate at a time, optimizing the circuit really just means minimizing the total number of gates. And it turns out this is essentially what existing like Boolean FHE pipelines do, right? So they start with some function, they compile it down into Boolean circuits, and then they optimize these circuits. Now, obviously, like, okay, so the thing we want to do is minimize circuit size, right? Build circuits with as few gates as possible. This is not a new problem. VLSI people have kind of been thinking about doing this sort of thing for decades. And so it's maybe a little bit surprising that like we have any valuable insight to offer here. Like what do we know that they don't, that they haven't figured out since the 1960s or whatever? And the answer is kind of, we know something about this space that they don't know, which is that this abstraction that I presented to you is kind of a lie, right? I mean, or this is an abstraction over what's actually going on under the hood, but it turns out that if we like peel back this layer and we look at what's actually happening in the scheme, we can do a lot better. So now let me tell you about the real CGGI programming model. Instead of thinking of our ciphertext as encrypting bits, we really want to think of these as encrypting small integers modulo like some small number n. So usually n is like 4 or 8, right? So your ciphertexts are like encryptions of integers modulo 4, let's say, or modulo 8. And now we don't have bits anymore, we have small ints. And so instead of thinking of the computation as being like evaluating a logic gate, we want to think of it as being this operation called programmable bootstrapping. So programmable bootstrapping gives us two sort of capabilities. The first is that we can arbitrarily add and subtract ciphertext as much as we want. And in particular, this means that we can compute whatever linear combinations we want over these ciphertexts. These combinations are linear over like z mod n, right? So it's still working modulo n. And the other thing that programmable bootstrapping lets us do, which is really the cool part, is indexing into a fixed size lookup table. So the size of this lookup table, or the number of rows, is determined by the modulus. So this is like a table with n rows. And what we can do is take a ciphertext and look up the element in the lookup table that corresponds to the value being encrypted by that ciphertext. And it turns out that with these two operations, we can sort of recover the abstractions that we had before. So in particular, now if I want to evaluate some kind of logic gate, I start by expressing it as a truth table. And then I take my inputs. I take this linear combination using powers of 2, so like 4x plus 2y plus z. And then I use that linear combination to index into my truth table. So zooming in on this a little bit, I've got a truth table for like this 3-way XOR. So let's say I start with the input 0, 1, 1. So x is 0, y and z are both 1. I can take my linear combination. So 4x plus 2y plus z is 0 plus 2 plus 1, which is 3. And that tells me to look in the third row of my lookup table for the output. Now, here we chose to use 4, 2, and 1 as the coefficients for our linear combination. And so we sort of implicitly made the decision to think of our lookup table as representing a truth table for a logic gate. But it turns out that we don't have to use these coefficients, right? I can take whatever linear combinations I want. I can add and subtract as much as I want. And so it turns out that if I let myself pick different coefficients, I get something that's strictly more expressive. So let me give you a little bit of intuition maybe on why this is more expressive before we dive into the details. So consider this example of consider this construction, I guess, right? So we've got 7 inputs here. All of my coefficients I'm going to set to 1. And so really what I'm doing is adding up 7 inputs, or 7 ciphertexts, and then using that sum to index into this lookup table. Now, if a lookup table has a bunch of zeros and then a 1 in the bottom row, it turns out that the thing that this computes is a 7-way AND gate, right? The only way for me to get the output of 1 is for all of my inputs to be 1. If anything is not 1, then I'm going to get something that's so this computes an AND gate. Okay, and so what we've done here is take 7 inputs, or a 7-input gate, and we've represented this with a single lookup table that only has 8 rows. So if you think back to like what our truth table abstraction would have required us to do, is with 8 rows, we would need multiple AND gates, right? With 8 rows, we can represent a sort of truth table that has 3 inputs, and so if I want to AND together 7 values, I need 3 different AND gates. Alternatively, I could try to think of this as one giant lookup table, so like 128 rows for 7 inputs. And we could build a 128-row lookup table, but it turns out the encryption parameters you need for that are kind of ridiculous. So that's generally not something you want to do. In contrast, this arithmetic lookup table, which is what I'm calling like sort of having arbitrary coefficients here. If I allow for arbitrary coefficients, I can evaluate this entire function just with one very cheap gate. Now, it is also worth noting that normally, like using all 1s for your coefficients is really bad because it means that you can't distinguish between the input 1, 0, 0, 0, 0 and like 0, 0, 0, 0, 1, right? These are in general, two different inputs, but if all of my coefficients are 1, they end up mapping to the same row of the lookup table. But it turns out that in the case of AND, we actually don't care about this difference, right? And is very highly symmetric. It doesn't care about what order its inputs show up in. And so in some sense, it has like these redundancies or these symmetries that we can sort of compress away and turn this like 128-row function into an 8-row function. So let me maybe elaborate on that point a little bit more by trying to build a lookup table for this other function. Now, drawing 128-row lookup tables is kind of a pain, and it takes up a lot of valuable slide space. So for now, we'll do this example in the context of a 3-input function that we want to represent with a 4-row lookup table, but just trust that the same sort of story holds for different values of 3 and 4. OK, so we've got this function, x0 and x1 implies x2. Now remember, traditionally, with our truth table abstraction, we would need 8 rows, right? Three inputs, 4, 2, and 1 are our coefficients, so we need 8 rows. But just like before, we have this like symmetry, right? x0 and x1, the function doesn't really care about distinguishing these. And so in some sense, we're wasting a bunch of rows distinguishing between different like inputs that only differ in what x0 and x1 are, even though f doesn't care. So for example, like 0, 1, 0 and 1, 0, 0, these are 2 inputs that the only difference is sort of swapping these first 2 inputs, but we're sort of, our coefficients are like, wasting a bunch of time trying to, or like a bunch of effort trying to put these into different rows when it doesn't matter. And so really what we want is to find coefficients that map indistinguishable inputs into the same row of our output lookup table. So for an example that doesn't work, let me explain the visual abstraction here a little bit. Normally we've had like one output going corresponding to every row. In this case, we have multiple outputs going to a single row, and so each box sort of has, multiple inputs going to the same row. So each box sort of holds like the set of all inputs that map to that row of the lookup table. So here, if I set all of my coefficients to 1, it turns out it doesn't actually work. Because, for example, this third row, like 0, 1, 1 and 1, 1, 0, will both end up, like these are 2 inputs that'll both end up in the same row, but they're supposed to correspond to different outputs. And so there's not like a nice answer of what output I should actually put in this row of the lookup table. But if I pick a different set of coefficients, 1, 1, and -1, it turns out that everything kind of separates cleanly, and now every row either has all greens or all reds. So every row has a well-defined output. All right, so clearly the coefficients matter. The next question is maybe like, given some function, how do we actually determine whether there is a set of coefficients or like what these coefficients look like? And the answer is like, in some sense, kind of boring. There's a lot of formalisms for this in the paper, but briefly, we start by framing this entire thing as an ILP problem, and then we ask an ILP solver to synthesize these coefficients. And so in particular, the ILP solver can either come back and say, yes, here's some coefficients I found, in which case we know how to build this arithmetic lookup table for the function, or it comes back and says, I couldn't find any coefficients, in which case we know that like this function is not expressible. Maybe it's not symmetric enough, maybe we need more rows or whatever. So now that we know how to express functions, how do we actually use these to build circuits? Well, we start with an ordinary Boolean circuit, right? So you can start with whatever program you want. You can use whatever Booleanization techniques you want to turn this into a Boolean circuit. And it's worth noting at this point, we are free to apply like the full spectrum of like all the work the VLSI people have done to optimize our Boolean circuit as much as we want. Of course, these optimizations will stay in the realm of this like Boolean gate abstraction, but we can apply whatever optimizations we want. And now we notice that we've got like 2 adjacent gates. And if we were to merge these, the total size of the circuit would get smaller, right? I went from 3 gates here to only 2 gates, even though this new gate is now computing a more complicated function. And in particular, like there's a problem here, which is that like this merged gate now has 4 inputs, which a priori needs like 16 rows if we think of our things as being truth tables. And so this merge is really only legal if the solver is able to find coefficients to represent this merged function. So with that, our merging procedure is we start with some circuit, we pick a gate in the circuit, and then we check to see if this gate can be merged with every single consumer. Right? So we ask the ILP solver if each of these merges is possible. If they're all possible, we perform all of the merges at the same time, and we iterate, either until we run out of gates to try to merge, or just like for a fixed number of iterations. Now, obviously, that step right there involves a bunch of calls to an ILP solver, and so this can be like very expensive and take up a whole bunch of time, especially if like, let's say you've got 10 merges to try, and like the 9th one fails, and you've like wasted a bunch of time figuring out coefficients for the first 8. So the paper has a bunch of heuristics and stuff that we like optimizations that we layer on top of this to help us like guess what things are going to be easier to merge. All right, so with that, maybe I can talk about some results. So the one question that we sort of wanted to answer here is like, how effective is this new abstraction at actually letting us represent circuits with fewer gates? In particular, how much can we like shrink circuits? How effective is this like shrinking procedure? So we took a bunch of common benchmarks, some like adds and multiplies, and then some like MPC stuff like set intersection and private information retrieval. We compiled these down into Boolean circuits. We applied some standard circuit optimization techniques. And then on these optimized circuits, we applied this merging procedure from the previous slide. And we found that merging lets us sort of reduce the number of gates by up to like 50%. Obviously, small circuits is not the only thing you care about. You care about fast circuits. So we did actually go ahead and like execute these generated circuits against an FHE library, against Open FHE. And we found that the actual speedups correlated very strongly with the reduction in the number of gates, which is sort of what you expect, because even though each gate is now computing a more complicated function, the underlying mechanism that it's using in CGGI is sort of the same. And so we don't expect these merged gates to be any slower. All right, so even with all of these like ILP solver optimizations and stuff like that, obviously like this compilation procedure is still going to involve calls to an ILP solver, and so it's going to be kind of slow. And so there's a concern like how well does this actually scale up to bigger circuits? So we tried playing this trick where you take some big circuit, you find some kernel that's repeated a bunch of times. So the orange things here represent like sub-circuits that exist within this larger circuit that are maybe identical. And I can try like pulling out a single copy of this kernel, optimizing it with the merging procedure that I described earlier, and then just like plugging this optimized thing back in. And so now I'm able to optimize this entire circuit without actually having to visit every single gate. And maybe this lets me like build a nice efficient library or like scale up to bigger programs. So the obvious question here is like, how well does this work? So we took a matrix multiply. We tried kernelizing it in a couple of different ways. And briefly, what we found is that different ways of kernelizing still give us like very comparable speedups to what our original thing gave us. So maybe the takeaway is that like kernelization is pretty good, and this helps us like apply this technique to larger programs as well. So in conclusion, the CGGI scheme traditionally models FHE computation using this Boolean gate abstraction, but we found that by changing our abstraction, we're able to represent gates that couldn't be expressed before, right? Once you fix a lookup table size. And in particular, we showed how a compiler can use this new arithmetic lookup table abstraction to generate smaller and faster circuits. With that, maybe I can take questions.
Hi, great talk. I'm Ajay from MIT. I have a question. So you used a metric of the lookup table size as an optimization metric, but is there a strong correlation between lookup table size and performance? Because some coefficients might be easy to compute, like 4 to 1 is just a bunch of shifts and adds, or even just concatenation of bits. But if it's like 3, then you have to do a multiplication.
Yeah, that's a very good question. So regarding the lookup table size, the size of the lookup table is something that, maybe I should have explained this better earlier, but the size of the lookup table is something that you sort of determine when you set up the encryption. So you set it up to say, okay, I want my ciphertext to be Z mod 8, and so now I'm restricted to 8-row lookup tables no matter what, and I can't go bigger. If I wanted to go bigger, I would have had to like change the entire encryption to encrypt Z mod 128 or something. The other thing about like different coefficients being easier, this makes a ton of sense when your things are actually bits, and so you have access to these bit shift operators. But it turns out that even when we're doing 4 to 1, we're still doing like x plus x plus x plus x plus y plus z. And so we're not getting like any real benefit from these coefficients being powers of 2, because these are integers and not bits.
I wonder if you could explain more about the setting here such that you expect you have a computation graph with redundant instances of the same computation, like allow you to get some benefit out of the kernelization optimization. In normal software, we would hope the compiler got rid of that redundancy and already only ran that computation once. So what's different about this setting?
Yeah, so the redundancy is in sort of the shape of the computation, not the actual computation. So maybe if I explain this kernelized benchmark a little bit better, we have a matrix multiply. In every iteration of the like innermost loop of the matrix multiply, you're doing an addition and a multiplication, right? And so you can pull out this addition circuit and this multiplication circuit and optimize these and plug in the optimized circuits, or you can essentially unroll your entire loop, get one giant matrix multiply circuit, and try to optimize that whole thing. So kernelization is sort of I mean, you can think like every time you have a loop, right? You can try to optimize the loop body, or you can unroll the loop and try to optimize the whole thing. So that's morally what's going on here. I don't know if that answers your question.
Yeah, thanks.
Maybe I have a question as well. So in logic synthesis, there has been a lot of work on standard Boolean optimization. And what they typically do is they create databases of all the LUT4, or they want to implement them. So they avoid recomputing the same thing multiple times if they see the same pattern multiple times. And I was wondering, in your case, can you give us an hint on how many of those, if I look at LUT4, for example, how many of the LUT4 would be implementable with an arithmetic lookup table of some size which is smaller than the number of rows than LUT4? In a sense, how do you pick the R and how much compression you get, and what is the space of Boolean function to arithmetic lookup function reduction that you get?
Yeah, so I don't have actual numbers on this, but I can give you some intuition. So first of all, regarding how you pick the R, the number of rows is something that you sort of pick when you set up the encryption itself. So this is not in general a configurable parameter. This is the strength of encryption that I want in some sense. But so the standard set of parameters that people use in the literature gives you 8-row lookup tables, for example. And it turns out that with 8 rows, obviously every 3 input function can be represented. Almost no 8 input functions can be represented. So you're sort of living in this range between 4 and 7. It turns out most 5 and 6 input functions have enough symmetries that they can be compressed down. 7 inputs is tricky.
Okay. Any other question? No? So we thank the speaker again.